Well, let's get started. Hi, I'm a PhD student at University of Exeter in the UK. I will present deep learning security for IoT. I will show you how to attack object detection models deployed on edge devices and how to attack image classification models deployed on cloud servers. The first two projects use Linux, while the third one uses Adversarial, which is a real-time operating system. So these are the three projects that I will present today. Let's move on to the background. Here's the research question. Is deep learning secure for IoT? We talk about deep learning security rather than cryptography. So we attack deep neural networks. In recent years, we see more and more deep learning applications on edge devices, such as autonomous driving. But here's the problem. What if deep learning models are vulnerable to adversarial attacks? Say, for example, on the left side, we have a pig, and it is recognized as a pig by the image classification model. If we add a small perturbation to the original image, we have another pig on the right side. From the perspective of human eyes, we cannot really tell the difference, right? This one is still a pig. Well, the image classification model classifies this pig as an airliner. So this is how we attack image classification model. We can add a small perturbation to the original image. The perturbation is unperceivable by human eyes, but the image classification model will make wrong prediction. Similarly, we can attack object detection models as well. So now you know that deep neural networks are vulnerable to adversarial attacks. Well, what does this mean for IoT? Can we attack deep learning models deployed on edge devices? Well, for IoT, IoT devices consist of high-end, middle-end, and low-end devices. For high-end devices such as Raspberry Pi, it can run Linux, and we can deploy deep learning models on it. We can also run the smart version of Adversarial on high-end devices. While for middle-end devices, such as 32-bit microcontrollers, we use the standard version of Adversarial. We will not talk about low-end devices such as Arduino, which is an 8-bit microcontroller, because they do not have enough memory to run an operating system. So we focus on high-end and middle-end devices today. I will introduce how we attack deep learning models deployed on both high-end and middle-end devices in real time. So let's move on to the first project. Adversarial detection, attacking object detection in real time. We tested our attacks in ROS Gazebo simulator. Here's a turtlebot in a simulated environment. The turtlebot detects the traffic sign using an object detection model. But we can fool the object detection model to detect traffic signs in the air. Well, let's see a real-time demo. So this is the turtlebot, the simulated turtlebot in ROS Gazebo. We can zoom in and zoom out. We can see the detection result here, and we can control the turtlebot from the terminal. The object detection model seems to be pretty stable, right? But this is not the truth. Let's generate some traffic signs in the air. As you can see here, now we have a lot of traffic signs being detected in the air and on the ground. From the perspective of human eyes, we know that we do not have traffic signs here, but the object detection model is fooled by the perturbation. Even if we move around the turtlebot, we still detect the traffic signs. So the attack is very strong and stable. So this is our attack in ROS. You can also test our attacks using a USB camera. Say for example, let's generate some objects on the right top corner. Now we have umbrella and, well, a person. In this demo, we only use CPU, so the attack is a little bit slower than the previous one. The previous demo uses GPU. So this is our first project. We can also attack the object detection model using a Raspberry Pi. And this is our second project, man-in-the-middle attack, a hardware attack against object detection. So as its name suggests, we apply the perturbation in the middle between the USB camera and the detection system. We use a Raspberry Pi to inject the perturbation. Well, here's a quick demo. We have a USB camera and a detection system. We use the Raspberry Pi to inject the perturbation. The Raspberry Pi reads the image from the USB camera, injects the perturbation, and then simulates a virtual camera to the detection system. The detection system has no idea that the image is manipulated. This is the original input image. Now let's inject the perturbation. After injecting the perturbation, we see quite a lot of objects everywhere. Unbelievable, right? Even if we move the camera, we can still detect a large number of objects everywhere. So, as I mentioned before, the attack is very strong and stable. We have quite a lot of objects. The attack consists of two steps. Step 1, generating the perturbation. Step 2, applying the perturbation. I will introduce each step one by one. In the first step, we generate a single universal adversarial perturbation to form all the images from the camera. As you can see here, our method generates more bounding boxes than prior research and has less variation. Prior research used the mean accuracy precision to measure adversarial attacks. Well, but it actually measures the accuracy of the model rather than the strength of the attack. So we propose 3 evaluation metrics to evaluate the attack rather than the model. After applying learning rate decay, we achieve much stronger attack, as you can see here. In the next step, as you have already seen, we use a Raspberry Pi to apply the perturbation. But here's the problem using Raspberry Pi. We can only apply the perturbation after the system boots up. Well, unfortunately, it takes roughly half a minute to boot the operating system or to boot Linux on Raspberry Pi. This is just too slow for our attack, isn't it? So we think, can we find a real-time operating system that boots up in milliseconds and is compatible with existing Linux applications? And we find RT-Threat Smart, which is a real-time microkernel operating system. Here's a brief introduction to RT-Threat Smart. It is smaller and safer. The kernel size is less than 500 kilobytes, and it can boot up in less than 500 milliseconds. It is much faster than Linux, isn't it? More importantly, we can take advantage of existing Linux applications to accelerate our development. Using RT-Threat, we can accelerate our attacks, but we are still working on it. We will release a demo of our attacks using RT-Threat Smart in the future. So this is how we attack object detection models deployed on high-end devices. Now let's move on from high-end devices to middle-end devices. For middle-end devices, we use the standard version of RT-Threat. This is a brief introduction to the standard version of RT-Threat. Using RT-Threat, we can use the existing file system provided by RT-Threat. We can also use some third-party packages such as a web server, telnet server, and we can even run very small deep learning models on RT-Thread. When it comes to deep learning security for middle-end devices, we cannot really deploy large deep learning models on these devices because we do not have enough memory. Under this scenario, we use deep learning cloud services. So for example, I will show you how to use these middle-end devices to send requests to the cloud service and get image classification results from the cloud server. This is the third project, Adversarial Classification, attacking image classification cloud services. As I mentioned before, for middle-end devices, we can send images to a classification cloud service and get the classification results using APIs. Well, unfortunately, image classification cloud services are vulnerable to adversarial attacks as well. Say, for example, here we have an image classification cloud service where we can upload images to the cloud server and receive the image classification results. Well, let's upload an image. Say, let's try a dog. We can choose different data sets. Let's recognize the image. And as you can see here, it is recognized as a dog with a probability of roughly 100%. Well, maybe let's try a different one. This time, let's upload a cat. And well, let's use the same Cypher10 dataset and the VGG16 model. It is recognized as a cat. Besides uploading the image from the website, we can also use the API to do image classification on microcontrollers so that we don't really have to deploy the deep learning model on the microcontroller. We can use the microcontroller to send out the request and receive the image classification result from the cloud service. Well, I will show you how to access image classification cloud service from microcontrollers using RT-Thread. So I will show you how to get classification result of using this small microcontroller. Well, hope you can see it. Let's do this from scratch. I will show you how to create a project using RT-Thread Studio. And later after that, I will write a program that sends the image to the image classification cloud service and get the classification result. So let's create a new project. So we can create a new project. Let's name this project to be Hello IoT. The development board I use here is ATK Pandora, which you have already seen. So let's create this project. The RT-Thread Studio will copy a template into our workspace. It may take a while copying the template, so let's just wait for several seconds. Now we can see a new project created here. If we open this folder, application, main, we can see the main file. Well, let's just compile this project. As I mentioned before, this is just a template, so it should compile with no error. While it is compiling, maybe we can start the image classification cloud service. The server I use here is actually an open source project on GitHub. The server can be started using Docker or Python. Here I will use Python. I have already installed Deep API via pipe install. So let's just start the server using the command Deep API. So as you can see here, the server is starting up from the terminal. By default, the web server listens on port 8080. So if we navigate to localhost port port 8080, we should see the web application. The server is still starting up. Oh yeah, it has started. So if I refresh the page, now we see the web application. Let's see if the program compiles. Oh yeah, it compiles. So let's upload this template project to the microcontroller and see if it works. We can see the output from the serial terminal. So let's open the serial terminal to see if RT-Thread boots up. Let's reset the boot. So as you can see here, RT-Thread boots up on this microcontroller. Now let's send out the request to the image classification cloud service. This is the image that we are going to send to the cloud service, a dog here. Well, before sending the image, maybe we can display the image in the terminal first. Well, we don't have to write this from scratch. We can use an existing package in RT-Thread Software Package Center. This is, if we search for VT100, this is the package that we are going to use. So we can use this package to display the image in the terminal. We can use existing examples. So this example displays an image in the terminal. If I press Ctrl S to save the configuration, the RT-Thread Studio will then clone this project from GitHub to our workspace. So if everything works fine, we should see a new package in the packages folder. So if I open this, as you can see here, now we have a new package here. Let's modify the example to display the image. We need to change, let's copy this image to our workspace first. If I click on open the resource directory, we can paste the dog image here. And we need to convert this JPEG image to be RGB format so that we can display the image in the terminal. Let's navigate to the folder and convert this JPEG image to RGB format using this Python script. Python followed by the file name. Now we have generated a header file. So let's change this one to docs. And we also need to change the weight of the height and width of this image. Yeah, that's it. Let's compile this program. If everything works fine, we can display the dog image in the serial terminal. Well, it may take a while to compile this program. While it is compiling, maybe I can show you how to display, how to connect to the Wi-Fi first. Because if we are going to send out a request, we need internet access first, right? So if we do a Wi-Fi scan here, as you can see here, we have several access points. This is the wireless network that we are going to use. Sorry, mistake. Let's recompile this project. This is the array that contains the image data, and this array is generated by the Python script. So this time it should compile with no error. As you can see here, let's upload this program to the microcontroller and see if we can display the image in the terminal. Let's switch to the terminal. We should see the boot up message soon. So RT-Thread is up and running. Now we can display the image using the command VT image show. Now we have a dog displayed in the terminal. Well, let's zoom out a little bit. So as you can see here, it's a dog, right? Even though it is a little bit small. Now let's send this image to the deep API. Similarly, we don't have to write everything from scratch. We can use an existing software package from the package center. If we search for web client, we should find the package. Let's add web client to our project. We can use existing examples. This example sends a post request to HTTP server. So if I press Ctrl S to save this project, now it is cloning this new project from GitHub into our workspace. So we should see a new project, a new folder here. So this is the package we just selected. And this is an example that sends a post request to this server. Well, of course, let's change this to be our server. We can first validate our post request using Postman. It is always a good practice to validate the post request first before implementing this on the microcontroller, so that we are confident with our request. So this is Postman. I will validate the post request here. This is the IP address of my local computer. Well, let's confirm this is my IP address. We can find the IP address here in the properties. The IP address is 254. Oh yeah, 254. And this is the body of the request. If I send the request, we should see the prediction result. By the way, this is the base 64 encoding of the same dog image. So as you can see here, it is recognized as a dog with a probability of 99%. Now that we have validated our post request, let's change the URL in this project. We also need to copy the post data. Let's copy and paste. The post data includes the image data. We need several backslashes here. 1, 2, 3. Yeah, that's it. We also need to change the content type because the image is encoded in a JSON format, right? Yeah, looks good. So let's compile this project. While it is compiling, let's show you how to connect to a wireless network. You have already seen several wireless network here, right? We can join a network using command Wi-Fi join. This is the SSID of my Wi-Fi and the password 2, 3, 4, 5, 6, 7, 8. Oh yeah, successfully joined. Let's check the IP address. So this is the IP address for the microcontroller. Let's see if this project compiles. Oh, we got an error. Don't worry, this is an expected error. So let's compile this program again. Oh, we got another error. It says region ROM overflowed by, well, several bytes. This means we do not have enough memory flash space for the program. This is a good chance to introduce how we change build settings in Artistry Studio. So if you open build settings, you can change the optimization settings. Say for example, if I change the optimization level to be optimized size. In this way, we can generate a smaller firmware. Hopefully, this will fit into the flash. So let's compile this program again. Well, it may take a while. Let's see if we have internet access. Let's ping google.com. Oh yeah, even though it took a while, we can see we do have internet access now. Now let's upload this program to the microcontroller so that we can send the image to the image classification service and receive the classification result. Yeah, no error. Let's upload this program. The program is still uploading. Oh yeah, uploaded. Similarly, let's first connect to the Wi-Fi first. Let's copy and paste. Yeah, connected. Let's check the IP address. Yeah, we do have an IP address. So we can send the post request using command web post. And yeah, we see the prediction result, right? Maybe we can make a small modification so that the prediction result is more clear. Say, for example, we can add an extra line here. If the buffer index is equivalent to a bracket, we can print an extra line here. We can print messages to the terminal using RT kernel print function. And if I compile this program and upload it to the microcontroller, we should see the prediction result in a better format. It is uploading. Similarly, let's connect to the Wi-Fi first so that we have internet access. And let's check the IP address of the microcontroller. Now we are ready to send out the post request. Yeah, as you can see here, now it looks much better, isn't it? As you can see here, it is still recognized as a dog with a probability of 99%. So this is a demo. Let's move back to the slides. In the previous demo, I showed you how to access image classification cloud services from microcontroller using RT-Thread. Well, but unfortunately, as I mentioned before, the image classification cloud service is vulnerable to adversarial attacks. In the next demo, I will show you how to attack an image classification cloud service. This is our last demo. Here I will initiate a black box attack against the image classification cloud service. This is the original image. As you can see here, it is predicted as a dog. Now I will add some perturbations to the original image. And after applying the perturbation, the dog will be recognized as something else. This is the original prediction. After applying the perturbation, the probability should drop gradually. So as you can see here, now the probability drops to 98%. We should see a successful attack in several seconds. Now it drops to 88%. 79. We are pretty close to a successful attack. Yeah. Now it is recognized as a horse. As you can see here, from the perspective of human eyes, we cannot really tell the difference between the image on the left side and the right side, right? While the dog on the left side is recognized as a dog, while the dog on the right side is recognized as a horse. So this is how we attack an image classification cloud service. Well, actually this comes to the end of my presentation. I demonstrated how to attack object detection and image classification models on both high-end and middle-end devices. We should really think about deep learning security while developing IoT applications. So this is the end of my presentation. The slides are available on this website, and you can find more information about RT-Threat by visiting Facebook, Twitter, LinkedIn, and YouTube. Thank you.